So, the chi-squared test. The idea of chi-squared is we're going to be comparing counts of things. I'm going to turn the lights on here because my lamp is getting really bad on my projector. So Taylor gets to sit in the dark. The idea with chi-squared tests, we use a chi-squared test when we're going to compare counts of things. By the way, it is chi-squared, C-H-I, chi, hard K sound, not chai as in the T. If you say chi-squared, you automatically fail the course. That's just the way it is. Okay? Don't test me on this. I will make it happen. So this is a kind of scenario here. And the Desmos activity, you'll get a different scenario. It's with rolling a die, seeing whether a die is actually a fair die or not. It's really kind of fun. So you open a large bag of Skittles, being somewhat compulsive, which I'm sure none of you are. You separate the colors and count them. I'm sure none of you actually opening a bag of M&Ms or Skittles actually separates. Okay, raise your hand if you separate the colors when you open a bag of Skittles or M&Ms. Who does it? I do it. I'm not going to lie. Ellie does it. Yep. Mm-hmm. The rest of you know you do it. You just don't want to admit it.
You're sociopath if you just throw them all in your mouth.
Yeah, I mean, yeah. Can you throwing all the colors of Skittles at the same time in your mouth? What are you, like, insane?
Yeah, no.
This is not okay. Even M&Ms, you know? You can't do that. It's not okay. So anyway, 60 green, 62 yellow, 80 orange, 52 red, and 70 purple Skittles you find. The manufacturer claims that all colors are equally represented in the bags. Do you have evidence to the contrary? So what we are doing now is we do tests like this before, but we do tests like just on the yellows. And so we'd have yellow and not yellow, and we could run proportions, right? Or just on the reds and red and not red and run proportions. But now I want to look at the whole array of colors that we have here and say, do the counts match what we would expect to see? This leads us to a chi-squared test. Now, a chi-squared curve is a distinctly non-normal curve. This is a chi-squared curve. Sorry, my phone is like getting warm in my pocket, and sure enough, yeah, I had a screen on, and it's very uncomfortable. I can tell my phone is being weird because it gets warm. I do not like having a warm phone in my pocket. That's very uncomfortable. Okay, this is a chi-squared curve. Chi-squared curve actually has a left end at 0, 0. So it is not infinite to the left like a normal or a T-curve. It is infinite to the right. It is skewed to the right. There is not just one chi-squared curve. There's a whole family of chi-squared curves. Okay? And they are based on degrees of freedom, which of course gets based on our sample size. And so they might, one chi-squared curve might be more like this, and another one might be more like this. But they're all skewed right. Even that one here, that third one I drew, which almost starts to look a little bit more approximately normal, it still has a definitive 0 point. So it's not nearly normal because it doesn't have two tails. It only has one tail. That tail is to the right. Chi-squared tests by their nature are always one-tailed. Okay, we're just measuring the area or the chi-squared statistic and the volume to the right. Okay, area to the right of that. The first test we're going to do for chi-squared, and there are 3 different types of chi-squared tests we can run. And the first test we're talking about here is called a goodness of fit test, or a GOF test. In your calculator, it's GOF test, GOF. So that's what we're looking for. In a goodness of fit test, there are going to be assumptions and conditions to consider. They aren't going to be that different from what we've seen in the past. The first one is important. This is kind of unique to chi-squared. We have to have a counted data assumption. So our data has to somehow represent counts of something. Chi-squared gets used when we have counted data. So it should be counts for categories of a categorical variable. We don't use chi-squared with quantitative variables. We only use it with categorical. Sometimes I get those words get mentally blanked in my mind, quantitative and categorical. I don't know why. Independence assumption, the counts in the cells should be independent of one another. In other words, no one item should be able to be counted in two different cells. Randomization condition, which should represent random counts, random sample from the population. Here we picked a random bag of Skittles, that's fine. Okay. The sample size assumption that we have a large enough condition that does apply here. And basically what that sample size here comes into the expected cell frequency. And that is we need at least an expected value of 5 in each cell. Okay? So we should at least expect to see a count of at least 5 in every cell. Now, sometimes we kind of violate this a little bit. We get one cell that gets an expected count of, say, 4.2. Okay, we're close enough. That's good. But if you start getting 3 cells with expected counts of like under 4, then we're probably not going to perform the chi-squared test. And again, this is kind of just like the expected large enough condition that we used with proportions NP and Q is greater than 10. Here it's just that it's greater than 5 for chi-squared. So every cell count expected value is going to be 5. And here's the interesting thing, and you're going to notice this. We kind of have to start performing our chi-squared test to know what the expected values are going to be. But we don't want to run our test until we know the expected values are going to be greater than 5. So we have a little bit of chicken and egg quandary here. Do we run the test before we know the expected counts because our test is dependent on the expected counts? Or do we, how do we deal with that? So generally what we do is we do have to actually start running the test to find out what our expected counts are and then go back and verify this expected count condition. We don't necessarily verify this before we do we actually start performing the test. This is when we have to kind of look at the data and then go back and confirm that this condition was met. We still do it in the A section of phantoms. It's just that we might have to work backwards to do that. We have a successful removal of the lid over here.
I needed to take a break, but now I'm good.
All right, she's better now. Now you gotta get that bottom one off. Good luck.
This should be easier.
All right, so the calculations, how do we do this? All year long, she got the bottom one in a heartbeat. We've been looking at this when we calculate a t statistic or a z statistic. We always said x bar minus mu, right? And I always have been rephrasing that in the entire year, the observed value minus the expected value, right? I mean, since we started this class, I've talked about that. Start with the observed value, which was like your x bar or your p hat, okay, or p hat, minus the expected value, which we said was mu or p. So we've been doing this all along. Observed minus expected. I've been kind of building us towards this test, using that same language all along so you'll see the consistency in what we're doing in statistics. These are differences, and the differences are actually residuals. So we know that adding all the differences, when we take our observed minus expecteds, and we add all those up, because these are residuals, we're going to get a sum of 0. So if you do calculate all your expected values, and we'll talk in a minute about how to calculate those, we take that observed minus expected statistic each time, find all those residuals, add them up, our sum is going to be 0, which means we can't conclude anything. It's a 0 sum. It's not very exciting. So again, we do this the same way we handled it in regression. In regression, we'd take the residuals and we'd square them. So we'd have a constant measuring stick, whether it was positive or negative. Squaring it eliminates that issue. So mathematically, that's a great trick, and we're going to use that one again. So once again, as we get into this whole chi-squared thing, we're starting to see ourselves revisit all these topics that we've done before. So we square them, and to get the idea of the relative size of the differences, we divide each squared difference by the expected count from that cell, from that cell, to and fro. All right, so this gives us what's called the chi-squared statistic. Each cell is going to have its own chi-squared value. The chi-squared total statistic is the sum. Look, this is a math symbol. Ooh, mathiness. For math people, yay, we have a sum symbol there. Very exciting. No, it's not an integral, so it's not like a calculus sum. We can do this using calculus if you really want. No.
Let's keep going for go.
It's just a simple sum of the observed minus expected squareds divided by the expected. Now, they do chi-squareds in like AP Environmental Science. They do chi-squareds, I think, in AP Psych, don't they? I can't remember. But chi-squared is a really common statistic that gets used. So, sorry, I really should, I'm distracted by a minute. They're trying to take something out the door right outside my window here, out the construction door, that's a little too big, right? And it's not fitting. And these guys are like, what? We're going to take the wheels off it. Okay, fun. So this is a chi-squared statistic. We've simply calculated the individual value for each cell and add those up, and then we're going to compare that against a critical value based on our degrees of freedom, depending on the level of confidence that we want to get. The chi-squared models, like I said, are a family of distributions indexed by degrees of freedom. We already talked about this. The degrees of freedom is not n minus 1, where n is like the number of Skittles. All right? N is not the number of Skittles in our example. N would be the number of...
Excuse this interruption. Would all seniors, letters A through C, please head to the library to exchange
Now
your
is my
laptop?
time, Mr. Dorn.
Perfect timing. Taylor's very excited to go change her computer. This is her big day. N is the number of categories, not the number of Skittles. So if I was going to look at my degrees of freedom here in my example, I have green, yellow, orange, red, and purple. I have 5 categories, so my degrees of freedom is going to be 5 minus 1, or 4. One of the most common mistakes with chi-squared is people will go, oh, 60 plus 62 plus 80 plus 52 plus 70, and get like this huge number of degrees of freedom, and then everything falls apart really badly. So remember, chi-squared is the number of categories, or degrees of freedom is the number of categories, not the number of individual statistics. The chi-squared statistic itself is used only for testing hypothesis, not for doing confidence intervals. Why, do you think? Well, because it's a one-tailed situation, right? Chi-squared by its nature, because it has that hard 0, 0 point, I can't do a confidence interval two-sided. It's always a one-sided test. So we don't do confidence intervals with chi-squared. The chi-squared, like I said, it's always one-sided. If it is large enough, we can reject the null hypothesis. So this is different from we're looking for a small p-value. You know, if the p is low, the whole must go. But here with a chi-squared, it's a large value rejects. Now that's backwards, I understand. But it's a completely different test, so the rules change. And I don't have any cute little rhymes for that. Maybe Nick can come up for something. Nick had that other one. Mechanics work like a one-sided test. Interpretation is always actually many-sided because you have so many different categories going on. So there are many ways the null hypothesis could be wrong. There's no direction to the rejection of the null model. All we know is that it doesn't fit. So with a goodness of fit test, all we're checking is does it fit or doesn't it? Actually calculating the chi-squared statistics, again, each model will give a hypothesized proportion from each cell. The expected value is the product of the total number of observations times this proportion. This is for a goodness of fit test. Finding the expected value in a independence test is going to be a little bit different. And we'll talk about that tomorrow. So what we need to do is find our expected values. Once we found our expected values, we can compute the residuals. Well, once we found our expected values, we can confirm the large enough condition. The expected values counts have to be greater than 5. Once we've done that, we can compute the residuals, observed minus expected. Then we square the residuals, compute the individual chi-squared components, and find the sum of all the components. Then we've got our chi-squared statistic. Next, we find the degrees of freedom. It's equal to the number of cells minus 1, and we test our hypothesis. And you can use your chi-squared statistic to find a p-value, so we still will find a p-value. So we're back to our, if the p is low, the whole must go. And large chi-squared values mean lots of deviation. So yeah, two ways that you look at chi-squareds. You still compute a p-value, so we still get our standard stuff going on there. But again, it's that large chi-squared value that gives us a low p-value, which just seems kind of funky, but it still works. Let's look at how this works. What's going on with our example here in just a minute. So our goodness of fit tests are likely performed by people who have a theory of what the proportion should be and who believe that the theory is true. The null hypothesis is only available for goodness of fit tests that the theory is true. As we know, the hypothesis testing procedure allows us only to reject or fail to reject the null. We can never confirm the theory is in fact true. We can only point out the data is consistent with the proposed theory. Remember, it's the idea of not guilty versus innocent. That goes all the way to the beginning. Or as I saw somebody post the other day for their AP stats, this is their theme. Accept nothing. We only reject or fail to reject. We never accept anything. So that's the theme in life for statistics. We accept nothing. That was fast.
Heck yeah! Zoom, zoom!
Zoom,
I was
zoom.
the first one in there.
Someone's kind of enthusiastic about this whole deal.
Yeah.
You guys are missing out by not being here today with Taylor, because honestly, this is like free entertainment right now.
Hey, but the only thing is they don't give you an adapter, but all my stuff is on a flash drive.
You can borrow mine.
Okay, I'll just bring it in on Friday then.
Well, you might not be here on Friday. You have your flash drive here?
That's fine.
So
Let's cry about it tonight.
you can cry about it tonight. So let's go back and look at our example. Okay? Let's go ahead and calculate our chi-squared statistic for our example. So what we'd want to do here is we have our colors. We have green, and I'm going to really upset the OCD people right now. Okay? So I'm going to make a table. Okay? And we're going to have our colors. So we have green. And we have yellow. And we have orange. And we have red. And we have purple.
So if you're trying to like angry or compare class, or
Have I upset the OCD people now? Have I really set you a little bit off? Good, good. My job is to poke people today, apparently. All right, so the observed count. So here we're going to take our observed count for each one. We've got this. Our observed count is 60 for green, 62 for yellow, 80 for orange, 52 for red, and 70 for purple. Now, this would give me a total, if I add all these up, that's 150, 202, 204, 264, 324. I add those up, and we have 1, 2, 3, 4, 5 categories, so 324 divided by 5. It'd be 64.5, or 64, 324, 64.8, I think. 64.8. So my expected value, because the expectation here is that every category would have exactly the same number of Skittles, 64.8. Now, I know, 0.8 of a Skittle, but that's okay. Let's work with it. Okay, which is still a 324 total. Okay, now we're going to take my observed minus expected. So 60 minus 64.8 is negative 4.8. This is negative 2.8. This is 15.2. This is negative 12.8. This is 5.2. And one way to check to make sure you've done your observed minus expecteds correctly is you add that, and the sum of that column should be a 0. So if you've done it correctly, because those are my residuals should add to 0. So then O minus E squared, and I'm doing this really slowly right now. So 4.8 squared. Now, nice thing is when I put these in my calculator, I don't worry about the negative signs because I'm squaring, right? So our 4.8 squared is 23.04. 2.8 squared, or 2.8 squared, I'll hit the right number, 7.84. 15.2 squared is 231.04. 12.8 squared is 163.84, and 5.2 squared is 27.04. Okay, then I have to take my O minus E squared divided by my expected value. So 23.04 divided by 64.8. Divided by 64.8 is 0.0355, or 0.355. 7.84 divided by 64.8 is 0.121. 231.04 divided by 64.8 is 3.57 or 565. $163.04 divided by 64.8 is 2.51, 2.516. And finally, 27.4 divided by 64.8 is 0.423. So my total chi-squared for this test is the 0.355 plus 0.121 plus 13, sorry, that was 3.565 plus 2.516 plus
Excuse
0.423.
this interruption. Would all seniors with
6.98.
last names beginning with the letter D as in David through G as in George, please go to the
Okay.
library to exchange your laptop.
So that's my chi-squared total for this test. Now, is that a big number? Well, let's take a look at this. We're going to go to our chart. Where did I put my handy dandy chart? Here it is. So we need our folder. And by the way, if any of you have not yet picked this stuff up, along with your card box, when you come in and pick up your computer, please pick that up too. It's on page 17. Now, what's my degrees of freedom going to be here? Well, I've got 5 categories. So my degrees of freedom we said is 4. So I'm looking at this 4. My sum is 6.98. So my p-value, my tail probability p, if I look at my chart here for 4 degrees of freedom, at 6.98, I am between 0.15 and 0.10 for 4 degrees of freedom. 6.9. So I don't know exactly what my p-value is based on my chart. I don't have an exact value, but I know it's bigger than 0.10 and less than 0.15. So if I want to decide whether to reject or fail to reject this, I'm going to say probably fail to reject at most reasonable levels. If 0.05 is usually my critical value, if my alpha level is 0.05, this doesn't give me a p-value of less than 0.05. It's bigger than 0.05. In fact, we know it's bigger than 0.10. So I'm going to fail to reject the null and say, no, I do not have evidence that the distribution is not equal for all colors based on this bag of Skittles. Okay? That's if we do it manually.
Of course.
And sometimes we will do it manually. More often what we're going to do is we're going to put our statistics into our calculator. So if we go to tests, it's tests D, chi-square goodness of fit test. And what they're going to want is they're going to want your observed minus your observed values and your expected values to be put in. Okay, so my list 1, so stat edit, I'm going to clear out my lists here because I got all sorts of data in my lists. List 1, I'm going to put my observed values of 60, 62, 80, 52, and 70. And in list 2, I'm going to put my expected values of 64.8 is all of them. Unfortunately, there's not a cut and paste here. Oops. Hit the wrong button. Okay. And then now that we have that data in, we go back to our tests. Chi-square goodness of fit test. We do have to tell it our degrees of freedom here. My degrees of freedom is going to be 4. And we're going to calculate this. And sure enough, look, it gives us our chi-squared statistic right there at 6.98. And my p-value at 0.13, which I said it was between 0.10 and 1.15. It gives me the exact p-value. And note, on mine on the bottom, it gives me my contributions from each category. So it actually gives me my chi-squared subtotals for row 1, row 2, row 3 on down to like 10 decimal places each. It's kind of a pain. But there it is on the calculator, quick and easy. By the way, if we were doing this test, we meet all the conditions, including the expected value condition, large enough because all our expected values are 64.8, which are all greater than 5. Generally, if we're stating the expected value conditions in a phantoms statement, we don't have to list all of the expected values. We just say the smallest expected value is blank, which is greater than 5. You don't have to list every one and say explicitly that, unlike NP is greater than 10, NQ is greater than 10, you have to list explicitly. For a chi-square test, it is sufficient to simply say the smallest expected value is blank, which is greater than 5. That's okay. That's enough. The goodness of fit test is the easiest chi-square test. And again, the key is making sure you got those expected values down correctly. So today, we're going to deal with that. That's our entire topic. Don't forget, if you haven't done the Desmos activity yet, to go back and check. I've got a link for it on Schoology from yesterday on the calendar. Just look in the Schoology calendar, it's there. Actually, the link is in, it's listed on Schoology. The link is actually in the AP Stats page. It's at the top of the AP Stats page, I think, of materials. That's where I put the link for this. But yeah, do the dice rolling activity if you haven't done it. It gives you another chance to kind of look at this whole chi-squared thing for goodness of fit. And everyone's results in the dice activity is a little different because you will roll the die, you will electronically roll the die, both the wooden one and the normal one, to see what your results are. So some people may get different results than other people. No two people's results should be exactly the same. All right? And we will start.